It should be recording. It didn't do the time countdown. Also, for some reason, it seems that I don't have my introduction slide here, but that's okay. Everybody turned in the first homework assignment. I believe everybody answered all the questions correctly, so that's all bueno. I will get a new homework assignment posted over the weekend. That homework assignment will include material from the lecture on Monday of next week, which is why I don't worry about getting in too early, because you won't be able to answer all the questions until after the lecture on Monday. Today we're going to be talking about ancient astronomy, a little history lesson. Yes?
Sorry, just so that I don't bring this up later. How do I find the textbook? Like, I was looking at Moodle and I didn't see like a link or anything.
I thought there was a link to the textbook. You can always just use the same link that you use for the physics class.
How do I find it? The OpenStax. So it's OpenStax?
Yeah. If you just look at their science books, the second one is astronomy.
Oh, so we'll look up like the AS whatever the code. Do we just look up the code?
No, go to OpenStax and then choose science books.
Oh.
The first one's anatomy, the second is astronomy. That's this.
Okay.
Okay, so obviously, I think to anyone, the sky has been visible since creation of man. And so all cultures have looked at the sky and they've noticed repeating patterns, and so we set up a timing system based on those repeating patterns. So some of the simple things that we do for these repeating patterns are the day. The day is based on the time for the sun to rise again, which now with modern astronomy we understand means the time for the Earth to do one rotation. And so we use the time for the Earth to do one rotation as one of our very basic measurements of time. And then we have the month. The name month is pointing to where it comes from, the lunar cycle. It takes about 29 and a half days, I'll have it on a slide here in a minute, for the moon to go from full moon to full moon. And so the period of the month is roughly based on that. It's not exactly, because you can't take 1 year and equally divide it into lunar cycles. And so different cultures have gone different directions on how they do that. Then we have the year. The year we use is the time for the seasons to repeat. And the seasons repeating is the result of the Earth going around the sun one cycle. So here is an ancient calendar, and I would have to sit here and stay to try to figure out whose calendar that is. But different cultures have different calendars because different people were looking at it and saw different organizational schemes. So why did it go to that? I have no idea.
That looks familiar.
Yeah. Actually, I do have an idea. This program overrides the button click. I need to turn it off. Now that that's turned off, the button click will do what it's supposed to do. I've already gotten used to this button click thing. See? There. So, yeah, here I've just talked about some of the options. The 7-day week was used long, long ago. Why do we have 7 days in a week? Probably because they recognize 7, quote, planets. 7 things that moved with respect to the stars. Now, those included the sun, hence Sunday. Included the moon, hence Monday. It's not really taking a genius to make those two connections. The other ones are a little less obvious, Wednesday or Odin's Day. I don't even remember which of them is tied to. Actually, I believe it comes from the Norse Woden. Thursday, one would certainly think that that's Thor. But the days of the week are, because of those objects, one for each one. And, well, that's a secular view. The Bible says that we have 7 days a week because in 6 days, God created the heavens and the earth and all that in them is. On the seventh day, he rested. So we have two possible stories. One has the Bible as its basis. The other one has conjecture as its basis. Obviously, I have more faith in the Bible than I have in the conjecture. But we do have the names tying in. There's the actual time to go from new moon to new moon. The lunar, this is, once again, you have 2 cycles for the moon. The sidereal time, the time for it to do 1 rotation, and then the synodic time, the time from full moon to full moon. So that's the synodic time. And I wrote, it's about 12 lunar cycles in a year. About, because of course it's not equal to, it's closer to 13. Actually, I say closer to 13. It's about 1/3. It's closer to 12. So the most common calendar, a solar calendar, just makes it a little longer than the 29 days. So that we have a calendar that basically does 30 or 31 days for every month. Just add a couple days to each month so that it comes out to 12. And then February gets shortened. But we also have lunar calendar systems. We're going to look at one of the prevalent lunar calendars here in just a moment. Calendars that are based on the moon. So the seasons cycle through the calendar. Right? The spring might start in this month one year and this month the next year, and it will slowly move through the calendar. Because it's not based on the sun, it's based on the moon. And then we have some hybrid calendars, like the Chinese and Jewish ones, that are based on both the lunar cycles and the solar cycles. And they do that by throwing in leap months periodically in the year. So you have 12 months in a year and you start shifting, and then you throw in a 13th month and shift back. Now, here is my favorite calendar. It's been proposed, it will probably never be adopted, but it would be awesome, especially for a school teacher, to make a calendar that has exactly 52 weeks a year. Now, how many days are in a year? Most years it's 365, right? Well, 365 is not evenly divisible by, what did I just say? By 52 weeks. It's 52 weeks, 7 times 52 would be 364. So you got that 1 day difference. So what do? You periodically throw in a leap week. So every now and then you would have just an extra week. Now, see, I'm a college professor here, right? My calendar is tied to the school calendar. So it would be proposed that you would just tie in that week. December gets an extra week there, between Christmas and New Year's, you have an extra week. Yes, as a teacher, I just have an extra week off. But the thing that would be beautiful about kids, I know it sounds like I'm self-serving here, but the thing that would be beautiful is you would have annual events, like Super Bowl Sunday. It would always be the same day. It would be every year the same date. You never have to say, well, what day is Super Bowl Sunday this year? And, everything else. I have my class syllabus. Let's say I'm lazy and I just do the same thing every year. I don't. I redo it every single year. But if I did the same thing every year, I wouldn't even have to do anything special. I would just not put the year on the schedule and photocopy away. It'd be the same schedule every year. That'd be great. I actually think it would be great. Let's go forward. Here is an Islamic calendar. Now, notice that's from 2005-6. I think it comes from a textbook I used to use. Today on the Islamic calendar is the 13th of Hijjah. Notice that I wrote it 2 different ways, Dhul Hijjah and Du al Hijjah. Hijjah is the month. And I'm probably pronouncing it wrong. Don't crucify me for getting the pronunciation wrong here. This is the last month of the Islamic year. So the year is just about to end. It doesn't match with our calendar, right? This is the month of the Hajj. In fact, the Hajj just ended yesterday. The Hajj is the pilgrimage to Mecca that every good Islamic person wants to do at least once in their lifetime. The calendar, notice this is 1439 is the year. Well, why would it be 1439 instead of 2018? Why are we in 2018? It's not the 2018th year of the Earth's existence.
Isn't it from when Rome established a calendar system, something like that?
It's not. In fact, it's going to come up in a slide later on. But it is somebody went back to calculate when they believed Christ was born. They were wrong by a few years, we now believe. And they said, let's set our memory system to start there. And so that was established more than 500 years after Christ. It wasn't established when he was born. And so that's why we have our numbering system. If you lived in Japan, you would be counting the years of the present ruler. So the present ruler was enthroned, when was it? It was somewhere like around 93 or something. And so it's the 20, I would have to do math, but I don't want to do math. But it's the 20-something year, and let's see, it's Showa was, I can't remember. Do you know anything about Japanese calendar?
I don't know anything off my head. I have one in my room.
Yeah, that doesn't help. I used to know all these things back when I went to Japan and all that, but yeah. So different system. Theirs is based on how long has this emperor been the emperor. So, when Hirohito was emperor, you had one numbering system. Then Akihito, he changed to a different numbering system. I found it interesting that war is banned during the Hajj. So for the last 3 days, there should have been no war with Islamic people. And the first month of the year, coming up in another 2 weeks, no fighting of any kind is allowed during that month. If there's any terrorist activity, any fighting in Syria, you know that they're not obeying Islamic law. But you know what we can be sure of? They're not. Because as with many of the Christian wars, the Pope is going to Ireland, I think this coming week or maybe right now. And there have been lots of battles between the Catholics and the Protestants in Ireland, all in the name of God. Right? It's not following God either. Okay, so we shouldn't just say, oh, they're not good Muslims. A lot of people aren't good Christians. Okay, so let's look at our calendar. The Roman calendar was developed about 200 BC, before Christ was born. And many of our months now reflect that calendar. And it originally had, we think, notice the word may have had 10 months and began in spring. Why would we think that? Well, let's look at month names, okay? Skip all the early ones, just go to the late ones. So like, after August, we get to September. What does sept mean? It means sept. So September should have been the 7th month. What does October, what does Oct mean? 8th. November, what does Nov mean? Follow the sequence. 9. December, what does Dec mean? 10, right? They're just numbering those months. Okay, now the Julian calendar. We talked about Julian calendar. Julius Caesar asked his astronomer to make a calendar that made some sense. It consisted of 12 months with days, 30 and 31 days alternating, with February getting short shrift. The actual days in a month have kind of shifted. Like, people took a day from another month to put in the month named after them to make it a more powerful, a more important month. So there's been some shifting. But that's basically what we have. The leap year system we already talked about. 365.2422 days in a year. The Julian calendar added a leap day every 4 years.
Sorry.
You know, there's power right there.
There he is? Oh! Sorry, I've been in this classroom not long ago.
Okay, and then the Gregorian calendar was updated so that it skips leap year every year that's divisible by 100, but doesn't skip leap year every year that's divisible by 400. So that it now has the average day, if you calculate over long enough time span, is 365.2425 days, is what our calendar does. So it's still not perfect, but the variation in the year, you know, we have little leap seconds every New Year's. That little variation is enough that we don't worry about going any further with calendar corrections. Yes, question?
I'm just curious, what is the Mayan calendar based off of?
I don't know.
Okay.
I know, especially when everybody's like, it's the end of the world! The big cycle's ending!
Because they're really accurate with their mathematical calculations with the calendars and stuff.
Well, all these ancient cultures are. We
They
tend
are,
to
yeah.
think that we're advanced and they're not. It's not so true. Okay, so our current calendar with the AD and BC started 532 years AD. So somebody said, let's go ahead and call this 532 AD. I can't imagine anybody doing that today. There's just too much, no, we've always done it this way. BC stands very literally for before Christ, before the birth of Christ. Now, in today's culture, we have a lot of people who don't want to reference Christ. And so they replace BC with BCE, which is before Common Era. So they're still using the abbreviation, almost the same, but taking Christ out of it. That's what you wanted to. Yeah. Okay, so BC before Christ, AD Anno Domini, or as we would say in English, in the year of our Lord. In the year of our Lord is, how old would Christ be, or how many days has it been since he was born? So, AD, Anno Domini, and once again, the people who don't want to use Christ, because AD is specifically referring to Christ, will use CE for Common Era. So, the Common Era means the era after Christ was born. Before Common Era is before Christ was born. It's still very much based on Christ, but you don't have to say. Now to some of these ancients. Aristotle. Well, heard of Aristotle, of course. He's one of the great thinkers, and he concluded from observations, from looking out there, that the earth was a ball. All these flat earthers, they've got issues with Aristotle. He's one of the people who started this whole ball earth conspiracy, if you will. Because he looked at the shadow that the earth casts on the moon during a lunar eclipse, and he said, that looks like the shadow from a ball. Now, of course, the sophisticated flat earther says that the earth must be flat because the Bible talks about the four corners of the earth. But then they say that the earth is pie-shaped. So that would actually match with this if they somehow believed that an eclipse was the sunlight being blocked by the earth. But no, they don't believe that. Flat earthers believe... It's baffling. Let me answer, Eli.
Well, I'm just, since you're talking about flat earthers, how do they explain how you can go around the globe?
They don't believe you can. No. Okay. Flat earthers. I can't believe I'm going to do this. It's like we have all kinds of time in class. What else are we going to do in class besides go to the internet and look up a flat earth map?
Do they ever look at NASA videos?
Oh, yeah, they believe they're all fakes.
I just saw a video the other day of this lady explaining where every country has a spot up there. like when they do like research and stuff, she literally showed outside the window. It shows the Earth as a sphere. So I'm like, oh.
Nope, that's bad optics on your camera. Duh.
Oh, that's what it was.
That's so weird.
Okay, this here is the standard.
They believe like the shuttles and stuff, those are all simulations.
Yeah.
Yeah, they think because NASA. Okay, you're taking a picture of something that's pretty big with a high resolution camera, which means that each picture is going to be like a small segment, and then they stick them all together to make the full picture, and they're all, oh, that's a composite image. That means artistic rendering. No, it's just putting together the pictures. Okay, where's that? Oh, great. It's just their little logo, apparently. Flat Earth proof. Great. Well, all I wanted to see was this. This is what they believe the Earth looks like. So they believe that we have the North Pole is the center of the Earth. And Antarctica is the edge of the Earth. You know why you can't go to Antarctica? Because they don't want any humans to get to the edge and just see that it's flat.
I really just want to send someone like all the way down, keep going straight one direction.
And you know, the simplest proof is simply that you can take a flight that goes from here to here. And that flight takes, something like 6 hours, which is much less than the time it takes to go from here to here and here to here. But I saw a flat earther very clearly dispute this. Said the flight doesn't exist. They just pretend it does.
So what's in the bottom? On the other side?
Well,
If it's the top, like what's in the bottom?
I thought it was.
Or something?
Wait, so think
That's
about
what the dinosaurs are.
I thought it was interesting because we had two pictures here that seemed to show something there. I don't know.
if flight doesn't exist, then how they like have, you can see airplanes in the sky.
Well, no, they just believe that that's a phantom flight on the manifest. That no aircraft actually fly there, that no people actually ever take that flight, but they put it on the manifest so that it looks like the Earth is a sphere.
So do they think that people just fly around in circles or something? Like,
Well, they just don't think that anyone ever flies from here to here. Well, they would say from here
but
to
there's
here.
people who do though.
It's not one of them. And if you were to pay for one of them to go do it, and he said, by golly, it really is, then everyone else would say, they paid him off, they bamboozled him, I know better. You would have to take every single one of them on that flight.
That's horrible.
Okay, come on, let's get back to astronomy. What did you say?
Oh my god.
Okay, so Aristotle used some good common sense to deduce that the Earth was a sphere back long before Christ was born. Aristarchus, notice the timeline here. This is on the ballpark of 250 years before the birth of Christ. Aristarchus used the time it takes for the moon to go through the Earth's shadow to determine that the moon is about 1/3 as big as the Earth, which is reasonably close. It's about 0.27 times the Earth's size. That's pretty close. Okay, 0.27 is closer to 1/4, right? But that's reasonably close. And you also estimate the distance to the moon by timing how long. Actually, no, I did that wrong. It was the Earth and moon shadows during an eclipse. So when you have a lunar eclipse versus a solar eclipse, to get the ratio of sizes, and then using the time, he estimated the distance to the Earth very close. Again, 70 Earth radii he calculated was the distance, and it's actually about 60. Real good numbers. He also went on to try to estimate the size and distance to the sun. Now on that, he didn't do so well. He said that the sun is only about 20 times farther away than the moon. Now that's not so different from the flat earthers. who say that the sun is far closer than we think it is. And so it's not nearly so big. It's a smaller light that's doing some pattern up there. Nobody knows why, as far as I know, or how it's doing that pattern, or how it's possible for the sun to always be overhead the flat Earth, and yet somehow it's below the horizon. But that's what they believe, okay?
I'm thinking about that. I'm like, oh my gosh.
Anyway, so he came up with the sun is only about 7 times bigger than the Earth. It's only about 20 times farther away than the moon. Those are not good. But he did some good work. Now, the whole idea of the Earth moving. The Earth moving historically has been a very sensitive topic. And Aristarchus had proposed that the Earth went around the sun. They should be all like, wait. I thought everybody believed that the sun went around the Earth. No. Aristarchus, more than 250 years before Christ's birth, proposed that the Earth went around the sun. But other people had good reasons to object. Good reasons, not silly reasons. We've been talking silly too much today. So what are those good reasons? Well, the first one is what we call parallax. Parallax is observation because of something appearing to move because of your motion. So let us take, it is Alex, right? Just want to make sure I don't say the name wrong. Let's take Alex's position. Right now, Alex is to the left as I view him from Eli. And if I go like this, now Alex is to the right of Eli. Neither of them moved, right? I moved. But there was an apparent shift in their positions because of my motion. That's what we call parallax. I know you guys are all young, but maybe you've seen a meter that has a needle on it, and the expensive ones have a reflective surface behind it. Have you ever seen out the reflective surface behind the needle?
I refer to the Spec 21s, like Spec 20s, spectrometers with the needles and like the mirrors that fit like.
Anything that has a needle indicator.
Okay.
It has a mirror behind it. Why does it have a mirror behind it? Since you know a specific device, you know why it has a mirror behind it?
So they can be more accurate in knowing what the value is.
It's so you don't have a parallax problem. You view it so you see the needle on its reflection, and then you know you're viewing from straight above, and you're not having a shift because of the angle your eye's looking from. So they argued that if the Earth was moving, that we would see parallax when we look at other things. But they didn't see any parallax. They didn't see any apparent shift in the positions of like one planet with respect to the next, or star with respect to the next. So they said it must not be moving because we see no parallax. There's also just the feeling. If you're sitting here in the car and somebody hits the car, you know it, right? You feel that bump. And they said that if the Earth was moving, we would feel the motion. We don't feel the motion, so we must be stationary. This is also used by flat Earth. Okay, they don't believe the Earth is spinning, clearly, because it's flat Earth. And so they're like, if the Earth was spinning, we'd all be dizzy, wouldn't we? Furthermore, shouldn't all the, by physics, shouldn't all the air fly away to ignore the gravity? Maybe the air should be still and the Earth is spinning. That's what a lot of them believe, that the air should be rushing at us at, over the speed of sound because the surface of the Earth is moving that fast. Never stopped to think that there might be some kind of, friction between the Earth and the air so that the air goes with the Earth. Just like in every display you see, like when you go to the exploratorium and they spin the globe and you see the fluid around it spin with it. It's fun. Somebody did you have a question?
So, parallax is like what you described right there with them, is
Yes.
when it's like, the positions didn't really move, but the position that you move caused it to look like it did.
So here, this example, you have a star that's closer and stars that are farther away. If the Earth moves, when the Earth is on this side of the sun, this star looks like it's up in those upper stars. And then when the Earth moves to the other side of the sun, this star looks like it's down with the lower stars. So the position of that star, the closer star, appears to have shifted with respect to the further ones. And so they didn't see that, and they said there's good evidence that the Earth is not moving. Well, just to counter that, we now have much better observational techniques, and we regularly measure parallax for stars. So we do measure that. And thus, one of the strong lines of refuting the Earth doesn't move is gone. How long has it been known the size of the globe? From at least 200 years before Christ, the size of the Earth's globe has been known. It was measured very accurately by Eratosthenes. He noted that on a certain day, the sun shone all the way to the bottom of a well, which meant that the sun was exactly straight above, what do you call the point straight above your head? Zenith, right. So the sun was exactly at the zenith. And so on the same day, he had the angle of a shadow measured in Alexandria, and that was 7 degrees. And so using geometry, he says, okay, the distance from Syene to Alexandria is, and I don't remember how many, he measured the distance in stadia, and that's 7 degrees, 7/360ths of a circle. Then all you have to do is take that distance between Alexandria and Syene and multiply it by 360 divided by 7, and that'll tell you the circumference of the Earth. And once you have the circumference, the diameter is just the circumference divided by pi. So he was able to calculate the diameter of the Earth to about 13,000 kilometers, which is almost exactly correct. So that the Earth is a ball with a diameter of 13,000 kilometers was known 200 years before the time of Christ. It wasn't some hidden secret when Christ walked the earth. So that's some background on ancient astronomy. Now we're going to move into more recent astronomy in the coming week. But now I want to shift to a little bit about observing astronomy. When we look at the sizes of things, what things can you with the naked eye tell have a size? When you're looking at astronomy, not, well, I see that car has a size. But in astronomy, what things? The moon?
Wait,
Stars you
well,
can't-
like shape, the shape, or what are you saying?
The stars, actually, all we see is a point of light.
Yeah.
George Bush was still president and makes some jokes about that. 1,000 points of light. There's one other thing besides the moon. It's more obvious, but we tend to not look at it. The sun. The sun and the moon are actually the only things that we can really see size to with the naked eye. Everything else is a dot. Now, if you use binoculars or a telescope, then the planets also are things that we can see size to. And also galaxies like the Andromeda Galaxy, we can see size to with a telescope. In fact, there's a lot of things with a telescope you can see size to. But stars, we can't see size to even with the telescope, other than the sun. Don't get all technical on me. Because they're too far away. When we're looking at the sky, the things that we do see size to are the separations between stars. And so we tend to measure those, and as scientists, you just measure the angle. You say there's this angle between this and this. So as an example, the moon takes up an angle of about 1/2 degree. Conveniently enough, so does the sun. And of course, you're a flat earth, you're about the same distance away, so about the same size, right? It's because they take up about the same angular size of 1/2 degree that when you have an eclipse, they just about perfectly fit on top of each other. It's not because they're the same size, because they're not. It's because their angle they make is the same. Now, small fact, but a really important one, the Earth goes around the sun in an ellipse. An ellipse is an oval. It's very close to a circle, but it's not a circle. So as I said in the last lecture, in January, we are as far from the sun as we get. And in July, we're as close, no, I said it wrong. In January, we're as close to the sun as we get. In July, we're as far from the sun as we get. And so if you have an eclipse that occurs in January, when we are closer to the sun, then the sun's going to make a slightly bigger angle. And so, for instance, if the moon passes between the Earth and the sun, the moon is probably not going to block out all of the sun. Now, the moon also does an elliptical orbit around the Earth, so sometimes the moon is closer, sometimes it's farther. So you can't just say an eclipse that occurs in January is going to have to be annular. Annular meaning you see that ring, the annulus of the sun around the moon. Because you have to take into consideration the distance from the Earth to the moon and the distance from the Earth to the sun. Now to math. You know there is math requirement for this class. And so here is our first math equation. A circle has 360 degrees. And if we have something like when we talked about the calculation done by Eratosthenes, he measured an angle of 7 degrees. And so he has 7 degrees divided by 360 degrees is the distance from Syene to Alexandria divided by the entire circumference. And so that's what this equation is saying. The distance between the two sides of whatever object I'm looking at, divided by the circumference it would make for a full circle, is the same as the angle it takes up divided by 360 degrees. So that's a simple ratio equation. And then we take this equation and we solve it for what is the size of an object out here if I measure its angle. And so you take this equation. Now notice for circumference I replace circumference with 2 pi. 2 pi d? 2 pi, should be 2 pi r. Why do I have 2 pi d? Oh, because d is not diameter, d is radius. I was a little worried there for a minute that I had a major mistake. D here was not the diameter, it's the distance from us to the object we're viewing. So just replace the circumference with 2 pi times the distance. Then solving for length, you just multiply both sides by 2 pi d, and you have the length, the size of this object, is 2 pi times the distance to the object times the angle divided by 360 degrees. We usually do some unit conversions. And so this is probably going to be new to you. I mentioned it last class period, but now we're actually going to take something to it. One circle, oh goodness. You know, it's too good to be true. It works in physics class, doesn't work in astronomy. I don't know why. It looks like it's going to work. See how the pin is lit up? Just pointing that out. It's going to work. I don't know if you saw, but there was a red light there. It wants to work. Okay. See? There we go. One circle is 360 degrees. 1 degree is equal to 60 minutes. We call them arc minutes when we're talking about an angle. And 1 minute is equal to 60 seconds. And so we can convert from degrees to arc seconds by using those conversion factors. So that's what I've done in this calculation. Notice this is solved for A here, so it has That would be solving the equation for A, and then just moving the two things with units of length together. The 360 degrees divided by 2 pi radians is what we're going to convert. And so 360 divided by 2 pi, and then 60 minutes per degree, 60 seconds per minute. If you multiply all of those together, you get a conversion factor of 206,265 arc seconds per degree. And so the angle in arc seconds is 206,265 times the size of an object divided by the distance away from us. So this equation here is an equation that, yes, we'll be using in our homework. And this equation is the same as this equation, is the same as what we had here. They're just different manipulations of the same thing. So that's an equation we're going to have to use. So let's think about a calculation we could do. The moon. .5 degrees is the angle it makes. And I don't know offhand what the distance to the moon is, or the size of the moon. I have to have two numbers to solve for the third, so I need to know one of those. So you got a calculator open, Alex. Just look up for me, what is the distance to the moon? 238,900 in what units? Miles? We never use miles, gotta tell you. Those are, no, that's fine, I'm not. So its distance is 238,900 miles. So I can take this equation now. I'm not going to use this number because that's already done the conversion. I'm going to come up to this equation here that's in degrees and say, okay, what is the diameter of the moon, the length of the thing we see? So don't tell us, we're going to calculate it. So if we take these numbers, the length should equal, let me change the pin color here. Let's pray that I don't screw anything else up. The length is equal to 2 pi times 238,900 miles times that angle, 0.5 degrees over 360 degrees. So now I just have to take, I've got a calculator here, handy calculator, 2 times pi, I don't think this thing even has, there it is. I don't know how to get it, oh well, 3.14159,265 is enough digits on pi, times 238,900 times 0.5 divided by 360. And so that gives us the diameter of the moon is equal to 285 miles. Now, Alex, do you have that as well? 2,085 miles. I hope that's right because that's what I got in my calculation. This calculator couldn't go wrong. What does it say?
Wait, what did you looking for?
The diameter of the moon in miles.
2159.
2159.
Yeah.
So it's not exactly right because we only had one significant digit there in the angle. So it's very easy to see. We've got plus or minus 10% built into that number because we only had 0.5. So it was in the accepted region. I don't know why I left this one in. We already talked about that. Looking at Aristotle's model, the celestial sphere model. Aristotle believed that you had that outer sphere is a celestial sphere with all the stars. That's why you see all the yellow things on it. All the stars are on the celestial sphere. And then you had crystalline spheres that were concentric about the Earth with different planets on them. And you notice those planets include the Moon is the closest planet, then Venus, then the Sun, then Mars, then Jupiter, then Saturn. How many of those? 1, 2, 3, 4, 5, 6. Oh yeah, I think the Earth would be the 7th for the 7-day week idea. So that's the basic model Aristotle had. Now that model had some significant flaws that Ptolemy identified. One of the first flaws is retrograde motion. Retrograde means backward. What in the world is retrograde motion, then? The planets, if you look at the position of a planet every night, you look at the position of that planet compared to the stars. You'll see that that planet is every night moving just a little east with respect to the stars. But you'll come to a time, oh, I don't have a picture of it. You'll come to a time when it reverses for a short period. That's probably what we're going to simulate for the first lab when we have bad weather. We'll simulate retrograde motion so you can see exactly why it occurs, according to Copernicus. But you have a period of time when the planet will start moving west instead of east on the celestial sphere. And then it will return to its normal eastward motion. And so the period of time when it's going west is retrograde motion. Now, nobody ever suggested, okay, somebody did suggest, that the planet's actually in reverse direction. And so what Ptolemy came up with was the idea of the planets aren't fixed on that crystal sphere. So let's go back to the crystal sphere picture. The planets aren't fixed on that crystal sphere. Instead, they're on this little wheel that is fixed to the crystal sphere. And that little wheel is rolling along, and the planet's going around a circle. And so it's kind of like the spirograph that I played with as a child. That the wheel is consistently going like, or the sphere is consistently going like this, and then the wheel is rolling along, so something at the edge is sometimes going backward, but generally going forward. So it goes like this. And so that's what this is illustrating. This looks a lot like the spirograph. Do you guys have spirographs as kids? I mean, because if I use an analogy and you're like, never heard of it, it doesn't help. And so you get a pattern like this. So it has retrograde motion during the time from here to here. It has prograde motion for all the rest of the time. So it's prograde from here to here, then it's retrograde from there to there, and then prograde again. Prograde meaning going forward, or in this case, going east. So Ptolemy came up with this improvement on the Aristotelian model. And he called these little circles epicycles. I think the deferent is the big cycle, but I didn't look it up before class. It was an explanation, and this model here dominated from the time about 150 years after the birth of Christ until the time of Nicholas Copernicus, which was, okay, I know I have it coming up. I've got to stop now, so I'm just going to find his. I'm looking for just the date of Copernicus. Here we go. Up until around 1500. So we're talking 1,400 years. The world believed in the Ptolemaic model, that we had these crystal spheres out there with these little wheels going on the crystal spheres that were causing the retrograde motion. Now, how can something last that long? I mean, our country is only around 240 years old. We're not even a fifth of that time. How can something last that long as a scientific belief?
Lack of technology to disprove it.
Lack of technology to disprove it. It made predictions that were correct to the best of their ability to measure. And so since it made correct predictions, people said, well, it must be true. It's making the right predictions. And so it wasn't until, actually, it wasn't Nikolai Copernicus that came up with the model that could make correct predictions. Copernicus came up with the heliocentric model. That's what he's supposed to be holding in his hand, is a little thing that shows the sun is the center and the earth out there going around the sun with the moon going around the earth. That's what that thing is. His model didn't make any better prediction than the Ptolemaic model. And so people didn't accept it. He also didn't publicize it very well because he was a Polish man. He was a kind of a clergy. And this Catholic Church was opposed to changing that view. So he wrote pamphlets out by hand and distributed them anonymously. And it wasn't until just before he died that he actually attached his name to it. So next class period, we'll pick up and learn about the Copernican revolution and actually the work of Galileo Galilei, or not Galileo Galilei either, of Johannes Kepler that actually convinced the scientific world to change the model.